Okay, so let's just do all of thermodynamics, a little crash course in it, to then derive this idea of densities, pressures, and sort of quantities that we should measure, right? So thermodynamics, we have, first off, we have the 0th law, right? And this allows us to define temperature, right? And all it says is two systems in thermal equilibrium have the same temperature. So the 0th law is usually forgotten, no one really cares about it, you only care about the first and second, but the 0th law, it's allowing you to define a temperature. It's saying if two systems are in thermal equilibrium, then they have this thing called a temperature, that they are the same thing. Okay? Now that you can talk about temperature, you can go and think, right? So now you have then we go into the first law. So the first law allows us to define a property energy of a system, right? And right, in differential quantities, it's right. You always know what it is. Some things I think are interesting about this is it's allowing you to define this property of a system called the energy of it with things that are not properties of it. These are properties of a process. But the algebraic sum of the two equals a property of the system itself, its energy, right? Neither of these things are inherent to a system or a box that you draw. They're things that are involved with processes that you're doing. But this is a property of my control volume, just the change in energy. What this means too is this variation is that it's path dependent. So this type of derivative is actually referring to if you have 2 points, 1 and 2, right? It's just saying, right, this dq is equivalent to all of these things, but they could be like path independent. They're path dependent. So, right, this is a dq, this is a dq as well, and this is a dq. So let's say it's 1, 2, and 3. This term right here means all of these actually have different differential terms because they were path dependent. It's called a variation. So that's this idea of different processes can give you different relationships, like an Otto cycle is this referring to how the path is defined. So this is also important because you have a dq and you have a d thing, we'll use it later. And then we have the second law. So the second law, what do we have for the second law? This allows an absolute scale for temperature, and it defines entropy, or a definition, right? It allows introduction of something called entropy, right? And what it says is, again, variation, change in energy is bounded below by a positive quantity, by a non-negative quantity, dq over dt. The absolute scale is coming from the fact that, right, you need this to be an absolute scale because if you're dividing by a temperature that you're at, you can't have this be 0. Right, so the idea that is there a 0, you can get really, really close to 0, but this is this absolute where you can have this. So this is where Kelvin, units of Kelvin. Right, not C, not right. So that's where this is coming from. Again, path dependence right there, but the change in entropy is bounded below. Right, equality holds. Right, so we have equality for quality for a reversible process. Okay, it's quality for reversible process strictly greater than for all irreversible processes. Okay, one thing to remember though is that all processes are irreversible. Reversible doesn't really exist. It's only like it's the best case scenario to analyze because it makes things easier. Mostly because you get inequality, not inequality. Equalities are easier to work with. Right? All processes are actually irreversible, but the question is by how much this is not true can let you really let you say, well, I'm going to treat it like a reversible process. Reversible processes are slow. They're essentially quasi-steady. So a reversible process slow, something called quasi-steady. Quasi-steady means you just link together steady-state solutions of differential equations, but these are just ideas that ways to categorize them. You also identify, kind of another way to say it. You could just look at the difference of these two things and go, well, it's basically zero. So if that's true, then you say have reversible processes. But you really have to use reversible analysis just because you get inequalities, you can actually write down equations because we don't know, it's hard to actually, if you have an inequality, we don't actually know a term that can tell us that proportion of how wrong it is. So you can't go, it's hard to go further in irreversible processes. Okay, so those are the three statements we're going to use to now derive quantities about densities and pressures, etc. One other thing is we have to define something called enthalpy, So enthalpy is this, boom, and then capital. Throughout all this stuff, if I use a lowercase letter, it means it's per unit mass. So lowercase internal energy. This is called internal energy. So lowercase means per unit mass. Okay. Always. Usually do it per unit mass. So enthalpy is this measure of internal energy plus pressure times the volume. And it's a quantity that's helpful when you're talking about things that can compress or change based on their volume, because it's the sum of the two. So you may not know one or the other, but you could track just the sum of both of them and then get relations about that. Sort of internal energy. What is internal energy? It's you could think of it as it's the molecular potentials. It's molecular potential. All the molecules that have these these Coulomb forces coming together. So the sum of all of those things can be a molecular potential force, and that's part of internal energies. Other types of internal energies, is you could have magnetic, any sort of internal, not external energy coming in, like you're pushing it, but all the molecular potentials and heat and things like that. So this U is sort of this giant thing you can track for all types of energies inside my system. But very helpful if we just derive this enthalpy being the sum of these two things. Okay, so we can use that first law, and we can combine the second and the first law first off to get this expression here. This is volume. Okay, so this is just combining. This is just going to be combining enthalpies. It's combining the enthalpy definition. It uses the second law and rewrites the first law to get this expression right here. This is people like this because temperature is a property of the system, entropy is the property of the system, pressure is, and the volume is. And it tells you something about the change in the internal energy of your system. Okay. So then there's sort of this U, this du, the internal energy. So then you can say internal energy, I'm going to say, is some function of entropy and volume, If I have some system right? Some blob with a bunch of molecules in it, and it has associated to a volume. And then also an entropy, right, it is associated to, right, entropy, a measure of the disorder of how many microstates can be thereof. So that's sort of internal to the system. Volume is inherent to the system. So it's reasonable to say that the internal energy is a function of these two, right, system properties, right? It could be related to the entropy and the volume. Okay, so now you do the famous thing in all thermodynamics is you just rewrite, okay, well then what's a differential of U? And you use that classical, right, linearization where you just add up, and then I have, yes? Right? So this is, you did this maybe in Calc 4, that is if you have a multivariable function, you just say, well, what's a little bit of change in that function? If you get really, really small enough in the changes, it just ends up looking like this, where I take the partial of this with respect to a constant b, so this is what the partial means. It means everything else held constant. Take a derivative with respect to entropy. Get this term right here, and get that term right there. Okay, so sort of the first thing I think is cool is just from this thermo relationships, we can just equate then coefficients. Right? See how this is just the second law rewritten, and this is based on the assumption that internal energy has to be related to entropy and volume. So you take my derivatives; these are the same, and then you go, wait a minute, look, right? This differential ds, this differential ds. So that means these coefficients must be equal, and that gives you a more thermodynamic definition of what these expressions are. So temperature, if you equate these coefficients, right? This is kind of neat now. Just from the first law, the second law, etc., you get that temperature really is a measure, right, of right, temperature is related to entropy. Maybe it's hard to really see that, but I think it's just neat that you can just get to that. Look at that, temperature is actually a measure of the rate of change of the internal energy of my system that you don't really know about with respect to the change of the entropy of the system, or right, the relationship of how many how many configurations could all these molecules have. And then same with this, pressure itself could be related to, right, a change in internal energy. So really getting a new sense of what pressure could be, and this is change in volume, right? There's a negative in there as well. So that's interesting too, that now this pressure term that we've talked about, all term, can be rationalized as, right, well, if I take a system, right, that has a volume, right, and I change its volume, pressure changes volume, right? You can squeeze it or compress things like that. Did the internal energy change? Right? And sort of that measure is pressure in a thermodynamic sense. So I find that kind of interesting. All this stuff we will use in a bit. I promise you, but it takes a while to get to sort of like interesting properties. So then you just kind of keep going. Next, you just actually take more derivatives, right? So I can take a derivative with this respect to volume, and I can take this derivative with respect to entropy. Okay, this carries over to there, and then you get this relationship called, I think we call it the Maxwell Relations, which we will use later, right? Maxwell's relations say that just from those two definitions here, we have and this is due to the fact that order doesn't matter in derivatives, right? So if you just took those derivatives, like I said before, you would get these relationships, and these are called Maxwell's. Maxwell, this guy from Maxwell's equations from electrodynamics, he was huge into thermos, actually, so he did a bunch of stuff. There's something called Maxwell's Demon that is super cool to YouTube if you have the chance. It actually took information theory to settle that paradox. Okay, so we actually have a little more tools now. We did the first law. We did relationships to get what pressures in terms of internal energies are. We have those things down. We have this thing that will come in handy before. It's just taking derivatives. Now, right, for compressible flow, one thing that's inherent in it is I just know that I will have little changes in density, okay? In my flow from going state to state, I know this thing, right, exists. In my equation of state, right, we have the ideal. I haven't even used an ideal gas law yet. But we're going to use this concept that the density is related to the pressure and the temperature. Okay, so before we move on, we're going to go, I have changes in density in compressible flows. How do I deal with that on a thermodynamical basis? So little changes, right? We're going to do our same thing. You should now be kind of getting a theme of thermodynamics is just doing this. You say, it's got to be a function of these system properties. Take little derivatives and do this linearization where you just sum up the partial terms. Okay, so then we have that. And what we do is we divide by. So a relative change, nothing more than this. Okay, I've just divided by rho to get something like a relative change. And then, right, if we want to also speak about volume instead of densities, it's really not anything special. You just actually have this relation here. So you're just kind of writing the same thing in two different ways. Yes. So this is now volume. This seems weird that you would do this, but it's important later, right? So same thing with a volume. Okay, I've just taken this and I've used the fact of definition of volumes, etc. Right in this way. Okay, right, because this is all just coming from that density is equal to mass of the system divided by volume. The masses cancel out in both equations. Okay. So we're getting to two sort of interesting things about things that we can measure, or beta and K are what they called. So we're going to rewrite now these dVs in terms of this relationship here, okay? And we're gonna rewrite these two equations again, but we're using this expression to get essentially some invariant quantities that have to be zero. So this D could be thought of as right, and then here. So before we go, we can go ahead and rewrite things. But if we do these calculations in terms of their equalities, we can get these relationships here. Okay, I'll do one of them. The other one's in the notes, but you just kind of see this neat little thing if you use this sort of differential, total derivative trick. So you go by the quotient rule on it. Okay, this is volume squared. Now, this goes away. Why? Because dm has to be zero for systems because of conservation of mass. Well, if the volumes and pressures can change around by, and I can't, right? Conservation of mass is a higher law, so that will stay. The dm has to be zero, right? And then I just get a negative m. I'm going to split this up. Okay, so I split this into two terms right here. Very similarly now, go back to the volume one, same calculations. Okay, this one becomes a negative m. Splitting it up again. Okay, and now I just divide both these by their right? Divide them both again, and what do I get? Rho, rho. So, okay, or negative 1. Okay, and that's important because you just get that this is to the negative of this, and this is to the negative of that through both sides of this differentiation. Okay, now if I take the last two equations and I now add them, right, this is what's important, is the fact that this quantity here is 0 both ways. If I did this derivative and did the laws, I'd get I'd get a negative of this, right, vice versa. So this has to be 0 sort of symmetrically, which is important. I had to do it both ways to say this. And now, if I add these two things, you get boom, boom. So carries on this one, and I get another coefficient. Okay. And this is just sort of where you happen, where this has to be identically 0 all the time. That means that these two coefficients must be identically 0 because this is arbitrary. So it's arbitrary change in temperature. But if it's identically 0, it's these quantities that have to be identically 0. Those are identically 0. We get sort of our two first thermodynamic quantities that are involved. So beta defined like this, right? Because if they have to, right, if the difference has to be 0, that means they both have to equal some, right, some value. So that's where this comes from. Okay, this is called the coefficient of volume expansion, and capital K. I've seen a kappa sometimes before. I've seen so these are sort of two things we just get from using only thermodynamic relationships about internal energies, and that densities has a state equation to it to get these two relationships, where this is a coefficient of volume expansion. And this is a coefficient of compressibility. Okay, so these are the two things. They can be measured, and they can be right for anything going off of going a little time. So we'll talk about my relationships with these things.